So the things that I wrote up on the board are the main topics that we covered before we left for our extended break or whatever this is. So I kind of wanted to run through some of those things, and then maybe we can do like a few sample problems from the packet. And then if you guys need me to go over anything else, I can do that too. So if there's anything in particular you want me to go over, just put that in the chat and I'll make sure I definitely cover that before we leave here. But what I think I'm going to do is I'm just going to go through the main things that we talked about before we left, maybe not in quite as much detail as I did before we left, but kind of just like review a little bit. So now when we first started talking about gases, we talked about the properties of the gases. We also talked about kinetic molecular theory. And really kinetic molecular theory is it's a theory that explains how gases should behave ideally. So it talks about their movement patterns and the kinetic energy, and essentially what it's really talking about is ideal behavior. So ideally, gas particles should be very, very far apart from each other. So they shouldn't really be interacting with each other. They should be spread out. They'll pretty much just keep moving until they hit either the walls of the container or each other. So ideally, gas particles should be very far apart. Now, anything that pushes them closer together leads to a deviation in ideal behavior. So if you have gas particles and you push them closer together, you're going to see a deviation in ideal behavior. So essentially, what that means is when we talk about the ideal gas law is this. The pressure times the volume is equal to the number of moles multiplied by the gas law constant multiplied by the temperature. Well, we should be able to plug those variables and then get a volume or get a pressure, okay? And we should be able to go and measure that volume or pressure, and then it should match, okay? But it doesn't always match, and the reason for that is sometimes there's a deviation in ideal behavior. So anything that pushes those particles closer together is going to lead to a deviation in what we should see based on our calculations. Now, the things that lead to deviations in ideal behavior, well, if you push them closer together, that can be caused by a lower temperature. So lower temperature means that the particles have less kinetic energy, so they move closer and closer together. Okay, that leads to a deviation in the ideal gas law. Also, if you have a high pressure, that will push them closer together. So if you can think, okay, does this thing lead to those molecules being pushed closer together? It could lead to a deviation in ideal gas behavior. The other thing that can lead to a deviation in ideal behavior is if you were to have a polar molecule. So if the molecules are attracted to each other, they're going to interact more with each other instead of the walls of the container, and they're going to move closer and closer together because they're attracted. So any of those things will lead to a deviation in ideal behavior, and that will change our calculated value of either the pressure or the volume. Okay, does that make sense to everybody? Do I need to clarify any of that? Also, are you guys able to use your mics? Because that should be an option. If you don't want to, I don't care, but you should be able to use your mic if you want. Okay. Okay, so the other things that we talked about, or the two other things that we addressed before we left, were the ideal gas law and then also combined gas law. So our combined gas law is this. So the initial pressure multiplied by the initial volume over the initial temperature is equal to the final pressure multiplied by the final volume divided by this. However, I don't like this. You guys usually do the math wrong when you have it presented like this. So the combined gas law, what I like to do is I like to move these from the bottom so that we don't have any kind of fractions anymore. So to do that, you need to multiply both sides by T1. That gets rid of that, or I'm sorry, yeah. And then what you have is P1 times V1 is equal to this. Okay, now we got to get rid of the T2, so multiply both sides by T2, and that gets rid of that. So instead of using this, which most of you will get the math wrong, you can just rearrange it to look like this. So the temperature would be on the opposite side. So initial, final temperature is equal to the final times the initial. Okay, so I like to use this, and this covers Boyle's law. Ooh. It covers Boyle's law, it covers Charles' law, and Gay-Lussac's law. So if you have this one equation, you can solve for any variable that may change. So if you change your pressure, if you change your volume, if you change your temperature, you can plug any of those variables into this equation, and anything that's being held constant, you can just take out. So if it's in the same container, the volume's not going to change. So you can just take that variable out. So I thought we could do a few examples of this. So I have a homework packet in front of me. Okay, so everybody should have the homework packet at this point. Even if you're not my student, you should have the homework packet. But let me do this. Let me share the screen, and then I can show the problem, and then I can work the problem out. So I'm just going to pick one, unless anybody has a particular problem on the first, couple of pages that you want me to go over that goes through ideal gas law. This is just like a review on the old stuff, okay? There we go. Okay, so let me pull up this. Can you guys see the homework packet now? Okay, cool. All right, so I thought we could do a few of these from the worksheet number 2. Does anybody have any of these problems that you'd like me to go over in particular? Otherwise, I'll just pick one. It's small. Is that a little bit better? Okay, so let's just pick one of these. We'll pick okay, so let's do number 3 really quick. Okay, so number 3 says the pressure in an automobile tire is 2 atmospheres at 27 degrees Celsius. At the end of a journey on a hot sunny day, the pressure has risen to 2.2 atmospheres. What is the temperature of the air in the tire? Assume that the volume of the gas has not changed. So I'm going to move this over here. Okay, so we're looking at number 3 here. Okay, so the pressure in an automobile tire is 2 atmospheres. So I know that this is a pressure because it's an atmosphere. So remember, pressure is going to be measured in atmospheres, millimeters of mercury, torr, psi, any of those things. This is also the initial pressure. This is the first one. So pull out all your variables. So this is 2 atmospheres. Okay, at 27 degrees Celsius, so this is my initial temperature. So this is going to be 27 degrees Celsius. Now, for temperature, it has to be in Kelvin. You don't have an option about this because we have to use Kelvin because Kelvin doesn't have any negative numbers. And you cannot have negative temperatures when you are dealing with the combined, or when you're dealing with anything with gas laws. So you're going to have to add 273 to it. And the actual number is 273.15, but don't worry about that. Whatever's on your reference sheet, just use that. So 273, that's going to give you 300 Kelvin. Then it tells us that our pressure has risen, so this is our final pressure. That's going to be 2.2 atmospheres. And we are looking for the temperature at that pressure. So we're looking for the initial or the final temperature. And you can assume the volume has not changed, so it's being held constant. So using our equation, we have P1 times V1 times T2 is equal to P2 times V2 times T1. Well, volume is being held constant, so take it out. And now you can just plug everything into the equation. So it's going to be 2 multiplied by my final temperature. And that's equal to 2.2 multiplied by 300. So make sure you're putting the temperature in the right spot. So the initial goes on the opposite side. So 2.2 times 300 that's equal to 660. So 2 times 2 T2, divide both sides by 2, and I will move this in just a second. You're going to get 330 for that. And that's going to be 330 Kelvin. So if the problem had been specific and said in Celsius, you'd have to subtract 273. Or if you had multiple choice, you want to watch your units. Okay, I'm going to erase this. And I cannot see the chat, so I have no idea. Okay, can everybody see like the work I'm doing, and you're good with that? Okay. All right, does anybody have any questions about that one? I think that one is pretty simple. You just really have to watch your units. You really have to make sure that you're using Kelvin. You don't have an option to not use Kelvin for gas laws. Cannot have a negative number, so it has to be in Kelvin, even if both the temperatures are positive. All right, so let's look at number 9. Okay, so number 9 says a sample of propane occupies 250 liters at 125 kilopascals and 38 degrees Celsius. Find its volume at 100 kilopascals and 95 degrees Celsius. So what we're going to do, we're going to pull out all the variables. We were given 250 liters first, so that's a volume. It's going to be my initial volume. I have that pressure at that volume, so it's going to be initial also, 125 kilopascals. And at the temperature, so the initial temperature is going to be 38 degrees Celsius, but I can't have that in Celsius, so I'm going to add 273 to that. It's 311. Okay, so now we have those variables. Find its volume, so we're looking for V2. And it's at 100 kilopascals, so the pressure here will be 100 kilopascals. Okay, and then we are at 95 degrees Celsius. So our final temperature is going to be 95 degrees Celsius. And that's going to be 368 in Kelvin. So add 273 to that. Okay, so now at this point, we're looking for one variable. This is combined gas law because nothing is being held constant. So we are going to keep every single variable in and then plug it into our equation right here. So P2 is the times V2 times T1. So if you guys don't mind, I'm going to start erasing. Okay, so P1 is 125 kilopascals, and we don't have to convert the pascals because they're equal on both sides. So if you have the same unit on both sides, it's fine. Okay, the only thing that this does not apply to is temperature, because for temperature here, you have to add 273. You're not multiplying or dividing by a number. That's the difference. Okay, you will get a different number if you leave it in Celsius. So our initial pressure is this. Our initial volume was 250 liters. Okay, and our final temperature, be careful, our final temperature is 368. Okay, we're going to set that equal to P2. P2 is 100. V2 is going to be unknown. And T2 is going to be 311. Make sure you're using the correct temperature. So, wait, hold on. Yes, okay, so our initial temperature is going to be 311. Our final temperature was 368, okay? So make sure that you are not flipping those numbers. All right, so now at this point, you're just getting your numbers. 125 times 250 times 368. That's going to give us 115,000,000. So that's 1.115 times 10 to the 7th. And then you have 100 times 311. Multiply those out. So let me do that. I'm going to erase all this. Times 10. It's 3. Alright, so divide both sides by 31100. Alright, and then V2 should be equal to 1.15 times 10 to the 6 divided by 31100. Alright, so you should get about 37 liters. Roughly. All right, so do we think that we're good with combined gas law? Because if so, I'm just going to move on. We'll do like an ideal one. And then anything that you guys have questions on, we can go over those. Are you guys good with like combined gas law? Like you remember how to do this now? I know it's been forever, and it's almost like you've never taken chemistry at this point. Ooh, we got 300 and... Did I have, hold on, 1, 2. Oh, you're right. Okay, you that's right. That is, it's supposed to be 369. I plugged in 1.15 times 10 to the 6th, and it should have been 10 to the 7th. So yeah, it's off by a digit. You're right. You're absolutely right. It's a 370 roughly. Let's see. Yeah. Okay, let's do number. Let's do. Okay, let's do number 11 and number 12. Because number 12 deals with number 11. Okay, so how many moles of argon are in 30.6 liters at 28 Kelvin and 658 millimeters of mercury of pressure? And then how many grams of argon are found? So with the ideal gas law, we know that we're going to use the ideal gas law as opposed to combined because nothing is changing in this one. So if you have a variable and you change the pressure, you change the volume, you change the temperature, you're going to want to use the combined gas law. So you would use this one right here. That's if something is changing. If nothing is changing, you're just using the ideal gas law. You just want to find one of the variables, so you're going to use this equation to do so. So the thing is, the universal gas law constant, we usually use this one. It's 0.0821 liters times atmospheres over moles in Kelvin. So you essentially, whenever you do math with the ideal gas law, whatever gas law constant you have, you want your units to match that. So R can be this. It could also be 8.31 liters kilopascals over moles in Kelvin. So if you have kilopascals, you're going to use the 8.3. If you have atmospheres, let's just use the 0.0821. So the first thing you're going to do, you're going to pull out your variables. So we're looking for moles. So that would be N. So I'm looking for the number of moles. I have a volume, and that's going to be 30.6 liters. I have a temperature, that's 28 Kelvin, I don't have to convert that. And then I have a pressure that's equal to 658 millimeters of mercury. Okay, so I have 658 millimeters of mercury. Well, if I look at my ideal gas law constant, I don't have that as a unit, that's not an option. So I'm going to have to convert it to either atmospheres or kilopascals. So let's go ahead and convert that to atmospheres. So I have millimeters of mercury on the top, so I want to have that on the bottom. Okay, atmospheres is what I want, that will be on the top. So 1 atmosphere is equal to 760 millimeters of mercury. I don't really expect you guys to memorize those conversion factors. Those will be given to you. So you should not have to memorize that. So 658 divided by 760, that's going to give me 0.8657 atmospheres. So I have that matches that. My liters matches here. I have Kelvin, and I'm looking for number of moles, so everything is matching. I'm looking for moles, so that's good. Now I can just plug it into the ideal gas law. So at this point it's just plug and chug. So pressure is going to be 0.8657 multiplied by my volume of 30.6 and that's equal to N, which we're looking for, multiplied by my gas law constant, multiplied by my temperature, which was 28. Okay, so 0.0821 times 28, we're going to get 2.29, 30.60 or 6 times 0.8657 is 26.49. Multiply or divide both sides by 2.29. And your number of moles will be this, 11.567 moles. Now, number 12 deals with this one. It's asking for grams of argon. So all you have to do for that's not Ag, that's silver. All you have to do for that is just do a conversion at the end. So I'm going to erase all of this. Okay, I have 11.567 moles. I'm going to convert that to grams. So grams is on the top, moles is on the bottom. 1 mole is equal to, oh, I do not have a periodic table in front of me. Argon weighs 39.9. So about 40. Thank you. Okay, so 11.567 times 40 is going to be 462.7 grams. Okay, so remember, if you're dealing with the ideal gas law, sometimes they will give you the grams, and then you'll have to convert that into moles, and that's going to be different every single compound, every single substance that you have. So if they give you grams, you're going to have to convert that into moles using the molar mass. Okay, so do I need to do any more problems for ideal gas law? So now I'm going to erase this. Okay, so do you guys want me to go over anything else? Because that pretty much covers the basics of what we talked about before we left. Yeah, so since you guys, all of my students, we've gone through KMT, we've talked about deviations in ideal behavior, we did combined gas law, we did all of the different gas laws too, Boyle's, Charles, Gay-Lussac's, and the ideal gas law. So technically, I'm not going to make you guys go back and watch those videos when you already have notes for them because you took them in class. So if you need to, they're there for you. And really, I just want you to do the pre-test, and then basically just check in with me, which you guys are already doing. After that, then you guys will go to Play Pose It and start watching videos for credit. Okay, so essentially you'll go to Play Pose It, and then the same thing that you do in class, you're going to take your note packet and then watch the video, take notes, and answer a few questions as it goes. And then that's for next week. So really the only thing due this week is going to be the pretest, which I said that you guys will have a second shot at if you need to. Okay, so you guys want me to do another ideal gas law example? Might just make up one. Okay, so let me go and pull up the packet again. And then if you guys have anything else in particular you'd like me to go over while I'm still here, you can just put that into the chat. Okay, so let's look at number 4. Number 4 is a good one. You have to do a conversion in there. Ooh, wait. Okay, so number 4. Hold on. That one you might not be able to do until you watch the video. Let me go back and look at that. Okay, so number 4 is a special type of problem. Wait to do that one because you need to watch the last video that deals with molar mass and also density. So just wait to do that one, okay? Let's do a different one that's just ideal gas law with not a combination of anything else. Okay, so let's do number 2. Okay, so number 4, you guys cannot actually do that one until you watch the last video. Okay, so don't worry about that one when you see it. Okay, so number 2, we're looking for moles of nitrogen. Okay, so we're looking for the variable N. Okay, and are present in 17.8 liters. So we're looking at a volume here. So my volume is 17.8 liters. Okay, we have our volume, we have a temperature. It's 27 degrees Celsius. Of course, we cannot have Celsius, so we're going to add 273 to that. 300, I don't know why, I just put that in the calculator. And then we have 1.3 atmospheres of pressure. Okay, so we know nothing here is changing, so we're going to use the ideal gas law. So pressure is atmospheres, we have Kelvin, we have liters. We also have our R. It's usually not going to be stated in the problem. You guys are going to have to just know that you need to look that value up on your reference sheet. So check all your variables, make sure they match R. Liters and liters, Kelvin and Kelvin, atmospheres and atmospheres, we're all good. So now at this point, I'm just going to go ahead and plug that into the ideal gas law. So my pressure is 1.3, my volume is 17.8. Number of moles, that's what we're looking for. Our gas law constant, multiplied by my temperature of 300. All right, so 0.0821 multiplied by 300, that's 24.63. 1.3 times 17.8 is 23.14. All right, and then divide both sides by 24. All right, you're going to get 0.93. Okay, so here's the deal. Okay, this is asking for moles. That was a nice problem. A lot of times they'll say, how many grams is this? So, nitrogen, if you remember, nitrogen is diatomic, okay? So if it asked you for grams instead of moles here, you're gonna have to go one more step and convert that to grams. But a lot of you are gonna forget that it's diatomic. So it's one of the Brinkelhoffs, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. So if it's diatomic, its molar mass is not gonna be 14, it's gonna be 28. So if I wanted to go an extra step, there's 28 grams for every 1 mole of this. That's going to be 26.3 grams. Okay, so make sure that you guys are paying attention. If it's asking for grams, make sure you're looking at it to see if it is a diatomic, because nitrogen gas is N2, not just N. but it didn't ask for that. This was a nicer problem. Okay, so I think, are there any other questions that you guys have about any of the basic gas law stuff? Okay, I'm going to take your silence as we know we have no more questions. So, if you guys need to reach out for anything, just let me know. Okay, this time also, it was different. It was supposed to be Thursday, but I actually have a doctor's appointment tomorrow. No, I'm not sick. I just need to go get my hip x-rayed. So, let me guys know if you, or let me know if you guys need anything. You can just send me a text or an email. And then I will post this on Schoology soon. I'm gonna like upload it and everything. Okay? All right. I'll see you guys later, okay? Bye.